talk about solubility product. When we think about solubility product, it's an equilibrium constant that's related to the solubility of an inorganic salt. So let's just consider a really simple ionic solid containing only monovalent ions, so MX, something, for example, like sodium chloride. Okay, that dissociates in solution to make our M+ ions and our X- ions. If we think about writing an equilibrium for this, we've got our equilibrium constant is then equal to the concentration of the products over the concentration of our reactants. That's normally how we'd write a sort of equilibrium constant for a chemical reaction. Now, our reactant, the left-hand side of the equation in this particular equilibrium process is a solid, so we can't have a concentration of a solid. So we basically leave that out, and our equilibrium constant is equal then to the product of the two concentrations of our species on the right-hand side of the equation. What we actually get then when we talk about the solubility product, so this is a product of the two concentrations. Actually, what we do when we talk about solubility product is actually use something called the effective concentration. So the effective concentration of ions in solution is often different from their actual concentration. This is normally actual concentration can be used at low concentrations. If you're talking about higher concentrations where the ions might be interacting together in solution, or if you're talking about biological systems where the ions might be interacting with organic species, say binding to them as ligands, then we have to consider the fact that the actual concentration and the effective concentration are different. Okay, so when we talk about the equilibrium constant, rather than using just normal concentrations, we use activities. Okay, so these activities, the effective concentrations of those two ions. Okay, so that's our final equation for solubility product. Okay, and what that basically means when we think about this is if a solid solute is left in contact with a solvent, it will dissolve until the solution is saturated. Okay, so you move to a point where you get to your saturation point is when this system here has reached equilibrium. Okay, so saturation is a state of equilibrium with the undissolved solute in equilibrium with the dissolved solute. Okay, so looking at that pictorially, this is our crystalline solid, for example, our MX or whatever it is that we're considering. There's our crystalline solid. We add water to that solid. Okay, so the solid is now in contact with solvent, and the solid starts to dissolve. So atoms or ions from that crystal lattice break off from the solution, from the surface of the solid, and dissolve in the solution. Okay, so when the rate of dissolution, that's all these arrows going out from the solid, is equal to the rate of reprecipitation, then the system is in equilibrium. Okay, so it's a saturated solution. Conversely, if the actual concentration, so that activity product, is higher than the solubility product, so the activity product at equilibrium, then precipitation will occur until the equilibrium constant, until the solubility product, is equal to the actual concentration. Okay, so this defines supersaturation, which we'll go into later. Okay, so pictorially, we've got our solid in contact with a solution. If we increase the activity product of that solution, so basically dump loads of extra ions into that solution, it's no longer equilibrium, okay, and we've basically pushed the equilibrium way over to this side, so we've got lots of the M+ and X- ions and not so much of this guy anymore, so push the equilibrium to the right-hand side. Okay, so it needs to go back to the left, the ions deposit onto the surface, and you get reprecipitation until you get to a state where the activity product of this solution is equal to the solubility product, i.e. the system has returned to equilibrium. Just a final note on this, the actual determination of actual values for solubility product is really difficult in biological fluids, basically because of the presence of all these organic molecules and different ions that might be interacting and changing the ionic concentrations, making them very, so basically this is why you have to consider activity, but actual determination of this is in such complex systems is actually really challenging.